In this video, I'll be demonstrating how to perform a dependent or paired samples t-test. Now, this is typically done when we have two groups of scores that we want to compare, but these scores are time dependent or are related to the same group of individuals. So, for example, we might have one group of participants who are being measured twice on an outcome, so like a pre-test, post-test design would be pretty typical, or it could be a crossover design in which we have the same group of people being subjected to two different treatments, and then we're comparing the outcome response based upon the result of those two different treatments. So either way, the important thing here is to remember that this is typically the same group of people being measured twice, as opposed to an independent t-test in which it's two different groups of people being compared to each other on a single measurement. So as you can see here, we've got two columns of data that we want to compare. And when we're doing a dependent or paired samples t-test, the data does need to be set up in columns next to each other. So each row represents an individual participant. And so this column here, B column, represents the first measurement on the outcome. And then the column right next to it represents the second measurement of the outcome. So let's say, for example, we're measuring the distance that someone can cover cycling over a set time period. And we want to compare the distance they could cover before the treatment and compare that to the distance they can cover after the treatment. So we want to see the effect of the treatment in a before and after situation. And so that's how the data would typically be set up in a paired or dependent samples t-test. It needs to be side by side in two columns. So our null hypothesis then would be that there would be no difference between the pre-test and post-test measure. And we would again use the same criteria we would have for any other hypothesis test. So in this case, we're going to use the p-value less than 0.05. And we want to test for statistical significance based upon the mean scores for the pre-test compared to the post-test. And what we're looking to see is the probability of those two scores being different due to chance being less than 5% or 0.05. So in order to run this analysis, we want to go down to the analyses menu. We want to find t-tests, and under that you'll see paired samples t-test. So we're going to click that option. So typically what we're going to do here is identify the two variables or the two columns that we want to compare. And typically these are temporal. There's an order to them. So variable 1, as we enter it, would be the pre-test, and variable 2 would be the post-test. If you're doing a crossover design in which you're randomly assigning the order of the treatments that the participants will be subjected to, that doesn't matter as much. But if you are doing a typical pre-test, post-test design, then you want to enter the pre-test in first. So in this case, we're going to go ahead and enter variable 1 as time 1. Click confirm. And then variable 2 would be time 2 or the post-test. And then we go ahead and click confirm. And that's all we need to do really at this point. So let's go ahead and click calculate. And we can see here the interpreted output, but what we really want to see in order to make our decisions is the raw output. And so we are going to have a table that's going to give us the result of the actual t-test. And so as we can see here, we have the mean and standard deviation scores for the pre-test and the post-test. And we have our t-score here. And then we have the p-value associated with it. As we can see here, the p-value associated with the obtained t-score is less than 0.05. So we would be able to reject the null hypothesis and say these two scores are different from one another. And we can also see here the Cohen's d effect size of 0.482, which is considered to be a moderate effect. But you may ask yourself, well, okay, did they do better in the post-test compared to the pre-test? And so we need to go back to the means to examine that. And we can see the mean distance covered at the pre-test was, let's say, 27 kilometers. And then the mean at the post-test was 30 kilometers. And so there is a 3-kilometer change from pre-test to post-test. And this change is statistically significant based upon the p-value being less than 0.05. So we'd be able to say that this difference is statistically significant. This is most likely not due to chance, that the treatment that we subjected them to created this difference. And the magnitude of that effect or that difference, we would consider it to be moderate. And another thing we can also look at is the confidence interval of the mean difference. So the mean difference was 3.2. We can ignore the sign here, and we can see that the lower limit would have been 5.05, and the upper limit would have been 1.4. So in the population, there's a 95% likelihood that the true difference after this treatment would range somewhere between a change of 5 kilometers and 1.4 kilometers. So that, again, you can use that to determine clinical significance along with the Cohen's d that we have. So in conclusion, then, we can conclude that the treatment did create a statistically significant difference from pre-test to post-test with a mean change of approximately 3 kilometers in this example. And then we'd be able to say that this goes along with a moderate effect size, which gives it some clinical significance. And then as we look at the confidence interval of the mean difference, we can see that the range of change in the population is actually fairly broad, and there's about a 95% chance that the true difference is somewhere between a 5 kilometer change and a 1.5 kilometer change, which may or may not be clinically significant depending on what that criteria would be. So hopefully you found this to be useful, and good luck using this in your own research.